before we look at how to do trig substitution, I want to talk to you about the 3 triangle issues, right triangle issues that you could run into. And this is dealing with the issue of you have a variable x and a constant a. Now, x could show up on the hypotenuse. Then a would be one of the 2 legs. What are the 2 trig functions that you could use to get x over a if x is hypotenuse and a is a leg? And yes, Pythagorean theorem is coming. But I just want to first focus on if you have your variable on the hypotenuse and one of the 2 legs is your constant, and you want it to be variable over constant. So hypotenuse over leg. Hypotenuse over leg. There we go. Secant or cosecant. Now, I ask you a question. Which do you prefer, secant or cosecant? Right. Know that you can use either. The standard issue way of explaining it is to just say, hey, if you see this, use secant. But know that technically you do have a choice. It's just we would prefer to use secant if we have an option. So if this is angle theta, then my adjacent side is going to be this one. And you can Pythagorean theorem your way to the 3rd side. What would that make this 3rd side? Square root of x squared minus a squared. Okay, situation number 2. Your x is on a leg, but your number is on the hypotenuse. So I'm going to put number on hypotenuse. As far as which leg the x goes on, what are your options? What 2 trig functions are you going to use depending on which leg has the x? Now it's sine or cosine. Which would you prefer? Sine. When I take its derivative, I don't get negatives, so it's preferred. That doesn't mean it's the only one usable. So if I call this angle theta, then I'm going to let x be the opposite, and I'm going to use sine. And if I Pythagorean theorem my 3rd side, what is this 3rd side? Square root of hypotenuse squared minus leg squared. Now, the third situation is both the variable and the constant represent the 2 legs. So what are my options if these are both legs? One of them is an opposite, one of them is an adjacent. What are my 2 possible trig functions? Tangent or cotangent. You can use either. Which would you prefer? We'd prefer tangent. So I want you to realize that all 6 trig functions can be used. These are the standard 3 that get used because their derivatives don't bring out negativity. But that doesn't mean the math requires you to use these. So I'm going to put down opposite over adjacent. And what is the 3rd side based on Pythagorean theorem? square root of x squared plus a squared, or if you prefer, the square root of a squared plus x squared. And now I want you to take a look at these three Pythagorean theoremed sides. One of them is an addition. And do you see why addition points you to tangent when you look at this triangle? Granted, it could be cotangent, but I'm going to be adding legs together when my variable and my constant are my legs. If I have a subtraction, though, I have a subtraction on a third side, and it's always hypotenuse squared minus leg squared. So taking that into account, if I have a constant squared minus a variable squared, do you see, first of all, why you want the constant on the hypotenuse? And that if your constant is on the hypotenuse, and then x takes one of your legs, that's going to mean you want to use the sine function. That is, unless, okay, question. Do you want to take the derivative of, this is side note, would you rather take the derivative of x divided by 5 or 5 divided by x? Take a moment to think about it. There's a reason why you want this setup. Jackie, are you serious? Okay, you have at it, Jackie. So also part of the reasoning of the setup is taking the derivative of just a variable divided by a constant means the derivative is just 1/5. Here, derivative, you're not going to get a logarithm because that's integration. You're going to take the derivative and you are going to get that. We don't want that. We really, really don't want that. So that's why these are the three best choices. And I think it's really important for you to know that you have a variety of choices. Why are these the better ones? And I want to also emphasize the hypotenuse issue. If you have the variable leading the subtraction, you have the variable on the hypotenuse. And if you want to write it as variable divided by constant, that means you're using secant or cosecant. If your constant is the hypotenuse, then you want it to be leg over hypotenuse so that the derivative is easiest. Now, the textbook gives you this summary. Now, while I didn't mention the issues of angle range, you should be aware of the angle ranges of inverse functions, of your inverse trig functions. But the main focus is, how do I work through solving the integral as a function without focusing on the domain of the function? The identities, that's just going to happen naturally. You just need to remember that when you see this show up in the integrand, you want to go with sine. When you see this show up in the integrand, you want to go with tangent. When you see this show up in the integrand, you want to go with secant. So let's do some examples. Here is example number 1. When you use trig substitution, most of the time you do have a square root in your integrand, but you don't always have a square root. As we go through different problems, I'll expose you to other situations. For now, most of the time you see a square root, and under that square root, you see something where, I'm going to throw this little tidbit out there. You could, by completing the square, create something that is a difference or sum of squares. But I'll roll that back and just say you see a sum or a difference of squares in a square root. Yes, that seems like a very rare occurrence, but it shows up, as you remember from that practice test. Oh, scroll up for a little bit. On the textbook or the triangles?
Yeah, this part, the textbook.
Okay. So whenever you see that, you think trig substitution, and then you figure out which of the 3 trig functions do you want. Okay, I'm going to scroll back to the problem, and this is in your textbook. Let me see if I can quickly find the page number to tell you. Page 467. On page 467 of the textbook, which, if you're in the Chapter 7 document, it's page 16 of the Chapter 7 document. All right, now for some fun, if my computer will do what I ask. All right. Come on, lag time. Catch up. There we go. Now, as you look at this, does a trig function come to mind? When you have a subtraction and the constant leads the subtraction, that's when you want to use sine theta. And while I do this, I want to point out to you that this is a type of u substitution. So I'm going to tell you that this is the u part of my u substitution. I pick a trig function and I set it equal to the function that is being squared divided by the number that is being squared. And I said that in a particular way for a reason. The function has the variable in it. Sometimes it's just the variable. So the function that is being squared divided by the number that is being squared. When we do a u substitution, we write down what u is equal to, and then we write down what du is equal to. Now, before, we could just say something like du dx and take the derivative. Here, though, we're kind of differentiating implicitly. But the implicit part of it, I'll explain in a moment. Let me first just do the derivative without saying too much. So derivative of sine theta is cosine theta. And then with the implicit part of it, I'm going to put times d theta. On the other side, I have the derivative of x over 3 is 1/3. And the implicit part is bringing in the dx. And now, if what I'm about to say is too much, block your ears. I'm going to erase this after I put it down, but I just want to point this out. You could look at this as implicitly differentiating with respect to t. If I do that, then I had times d theta dt and times dx dt, but do you see that I can then multiply both sides by differential dt and it's gone? And so it's not necessary to bother saying it. And that's technically what's going on when I do the implicit differentiation here. But all you need to do is come up with the trig function being equal to the function being squared divided by the number being squared, and then find the equation of the differentials. Now, you can do everything from here. But I want to tell you that something that's going to be extremely useful is that this isn't just any small time u substitution. Putting down sine theta equals x over 3 is a bigger equation than that. In fact, it is 6 equations in one. You can see all of the 6 equations if you draw a right triangle. It doesn't matter how you orient your right triangle. If the sine is equal to x over 3, and you remember that sine is opposite over hypotenuse, then you can do opposite over hypotenuse. And Pythagorean theorem gives you the third side. What is that third side? Am I having lag time again? There we go. Square root of hypotenuse squared minus leg squared. Do you notice that that is the square root that is sitting in your integrand? There are some really interesting ways you can go about this. I want to pause for a moment and let you just look at this and look at the picture and think about what you could possibly do. There's one thing that you must do. You must substitute dx so that we are in terms of theta. How you manage the rest of the integrand, there are various ways. And I want to give you a moment to look at that and think about it. I'm going to show you some different ways that you could approach it, but I want to first give you a moment to see what you naturally come up with. Now, the first way I'm going to do this is showing you kind of a minimalist look of all you need is the u and the du, and you can just shoot off from there. So if I have my u and my du, then I'll substitute into the dx, and I will substitute into the x's. And here we go. My x is equal to 3 times sine theta. And my dx is equal to 3 times cosine theta d theta. I want to pull this to the side. And I'm going to distribute my squared over the multiplication of 3 and sine theta. And take a moment to look at that square root, and do you recognize it? If you don't recognize it, oops, trying not to give away the answer. Do you recognize it now? Trig identity. Pythagorean trig identity. What does this entire square root piece simplify to?
Isn't it 3 cosine theta, which you could have, in looking at the triangle originally, kind of just
Yes, exactly. That's why I wanted to pause and have you just kind of look at the possibilities before I started showing you some possible directions. Because
if that one side of the triangle is basically the numerator, you could just say it's like multiply it by the length of the hypotenuse.
Mm-hmm.
It's just 3
Right.
cosine theta.
Right. And people think differently. Some people prefer this minimalist technique. Other people prefer to look at the triangle and see some shortcuts based on that triangle. And it's up to you. Whatever works better for you, use it. So I'm going to go back to my integral and put that in. And now I've gotten to a particular point. This is the point where it turns into a trig integral. And I may want to do some simplification until I figure out the best approach. But at that point, it's a trig integral. Now, I want to, before I go through that trig integral, show you other possibilities, clearly write out other possibilities of how you could have dealt with this, because it's really awesome to see the different ways that you can go about it. So I'm going to erase. I want to repeat, you have to have the u and the du. Then if you want, you can simplify things a little bit if you take the side that has the square root divided by the side that has the constant. And recognize what trig function that is. It's adjacent over hypotenuse, so it is cosine theta. And that will allow you to substitute into this whole piece 3 cosine theta immediately. But you know what? There are other ways you can play with this too. Did anyone see other ways that they could play with it? And what I'm going to do is I'm going to write that integrand. The dx must be substituted into. I have no choice on that. I must replace dx with 3 cosine theta d theta. From there, do you see some different possibilities of how to manage? If you look at this right triangle, do you see where this is going? If I look at my right triangle, the square root side divided by x is which trig function? Cotangent. And then when I look at the 1 over x and then go, hey, you know, there's a 3 right there too. That seems a little too convenient. Three divided by x is which trig function? You've got hypotenuse over adjacent. I'm sorry, I said adjacent. Opposite. Hypotenuse over opposite is the reciprocal of sine. And then you still have times cosine theta d theta. So there are just so many ways you can do these and get creative with that triangle and have fun. But once you get to the point of the trig integral, then it's a matter of what do I have? How do I work with it? And let me insert some space. If we're looking at it from here, then I might see that I have 9 cosine squared theta over 9 sine squared theta d theta. I can't say that that's necessarily a format you wanted. So how else could I write it? I could recognize that that's the same thing as cotangent squared. And if you stick to a more minimalist memorization, then cotangent and tangent get to do the same basic thing. So think for a moment, if you saw tangent squared, what direction would you want to take? And keep in mind, our hopes are for an odd exponent on sine, cosine, or tangent, and an even exponent on secant. I don't have that, but when tangent shows up with an even exponent, it's manageable with the trig identity, the Pythagorean identity. And that Pythagorean identity says that tangent squared is equal to secant squared minus 1. What is cotangent squared equal to? Cosecant squared minus 1. And cosecant squared is the answer to the derivative of negative cotangent. And then I have a minus 1. So I have a minus theta plus c. And I am not done. If those thetas were used, you might realize you still have to go back to the original variable. Before I do that, I want to point out to you that if you play around with this trig, you're going to wind up with exactly the same thing. And also, if you find yourself in a desperate situation where you don't know where to go with your trig integral, convert everything to sine and cosine, and you might see it a lot better. So cotangent being cosine divided by sine, cosecant being 1 divided by sine, and then your cosine theta. And that would take you to this point over here, where you could hopefully recognize what to do at that point. So I'm going to take the answer, negative cotangent theta minus theta plus c. And now I need to convert it back into x. If you have drawn this right triangle, you can just look at it and go, cotangent is adjacent over opposite. Or maybe you think, cotangent is tangent's reciprocal, so I'm reciprocating opposite over adjacent. Anytime you have a trig function and you need to convert back to the original variable, do not bring in an inverse trig function. I don't want to see a cotangent of an inverse trig function. It should be simplified. But when we run into just plain singleton theta, the only way to convert back is through an inverse trig function. Now, technically, you have 6 options. The textbook is only going to use 1. They're going to use the original U choice. So inverse sine of x over 3. And we are done. At this moment, this may seem like an incredible amount of work. But as we continue to do these over and over again, you're going to become so much better at your trig. And this is going to go faster as you become stronger with your trig. And that is the thing I find absolutely to be the most valuable thing of these particular 2 advanced integration techniques, with trig integration and trig substitution. Maybe our computers can solve these integrals for us. Additionally, there are set formulas that you can use instead of going through this process. But going through this process forces you to become stronger in trig, which is extremely valuable on its own. All right, moving on to a second example. We start all over again. So I'm going to give you a moment to look at it, write it down, think about your strategy. And don't forget to constantly hydrate. I say that because I've been forgetting to hydrate. So I happen to have a square root, But I want to say again, we don't always have a square root. What you're really looking for is a sum or difference of squares. And with those squares, one of them is a square of a function. One of them is a square of a number. So if I take the function that is being squared divided by the number that is being squared, which trig function should I choose? I could choose cotangent, but this is your best option. Now, if you want, you can right away draw your triangle and see all the functions that this creates. That also allows you to make sure that you chose the right trig function. Because if you chose the right trig function, this is going to show up. So tangent is opposite over adjacent. Pythagorean theorem gives me square root of leg squared plus leg squared. And with the Pythagorean theorem, I am getting this. And that was intentional. So realize that I am doing a u substitution. This is my u. I need my du. Derivative of tangent is secant squared multiplied by the differential d theta, and then derivative of x over 2 times the differential dx. The one thing I must substitute is the dx. From there, it's however you want to go about it. If I replace this x with 2 tangent theta, I need to remember to square it. For this square root, I can either go, well, that's the square root of quantity 2 tan squared, or 2 tan theta squared plus 4. Square root of 4 is 2. And the square root of tangent squared plus 1 is secant. Or I could look at my square root side divided by my constant side. We have 10 minutes. Is hypotenuse over adjacent, which is secant. So one way or another, I end up with the same trig integral. And then after that, it's a matter of simplifying the trig and determining what's a good direction to take. So now trig substitution is over until we have to go back and put the original variable back in. And we're on to trig integration. I like to deal with my constants early on before I mess up. This way I have it written, I'm going to mess that up. No, not that. There we go. Now I won't mess it up. Wait, wouldn't what be 2 secant OP? Okay. Well, come on. Would you listen to me, my pen? Okay. Those 2's cancel. I do have this 2 being squared. And then I've got also a canceling with one of the secants. And now I have a secant in the numerator and a tangent squared in the denominator. And now I've got to decide what direction should I take. And a lot of times you actually just would prefer to just convert everything to sine and cosine. So let's do that. What is secant in terms of sine and cosine? What is tangent in terms of sine and cosine? And let's simplify. And then take a look at it and think, how am I going to get through this integration? And I've got to tell you, it is surprising how many times there is more than one way to get through your integration. If you follow the rules, you notice in your numerator you have an odd exponent on cosine. And in that case, you can get through this if you make u its partner sine theta. And then I have u to the negative 2, integrating u to the negative 2, u to the negative 1 over negative 1. And then that u is sine theta. And then I've got to go back to the original triangle to figure out what that is. Before I go back up there, though, did anyone see another actually faster way to do this? That's the hint. Yep. So what is the integral of cotangent times cosecant? That's the answer to taking the derivative of cosecant negative. And do you see that those two are exactly the same thing? Isn't that fun? There are so many ways, so many small little different pathways you could take through this problem. And I find that much more interesting than just something that has a very particular way to get through it. So I've got negative 1/4 cosecant theta. And when I look at the triangle, I can remember that cosecant is sine's reciprocal. So hypotenuse over opposite. Whoops. And then I can't write opposite, apparently. And voila. How awesome is that? I'm double checking our end time because I can never remember on Friday. We have until 12:45. And okay, that's 2 minutes away, and I don't see getting through enough to bother starting something right now.